All right, so remember that the worksheet for 3.5 is pretty comprehensive. A lot of good old free response questions that cover some algebra pre-calc questions like symmetry and roots and stuff like that. Just remember the roots of a function f are the x-intercepts. The roots of the derivative are the critical values, and then the roots of the second derivative are the pivotal values. Okay. Happy granola bar day. The word of the day is contumacious. It's a really good word. Contumacious is someone who's willfully obstinate or disobedient, almost to the point of disrespectful, like a jerk. And so there's really two vocabulary words in one right there, right? Contumacious is one, and obstinate. Some people in the last period didn't know what obstinate means, but obstinate means stubborn, right? Okay. And then I got you 4 rebus puzzles to make up for it. So we're doing optimization. Optimization is nothing more than finding the absolute max or the absolute min in a word problem, okay? We get to write our own equations most of the time. So I did skip this one here, the ladybug farmer. We just kind of flip it on its end. Let me at least talk about example 4. I don't think I'll work all the way through it, but it's the same ladybug farmer, but now we're changing it around. He wants to enclose exactly 10,000 square inches. So in the previous problem, he had 500 linear feet of fencing, and that was the constraint. Here, the constraint is we need exactly 10,000 square inches of grazing, and he'll go buy whatever amount of fence he needs, but he doesn't want to buy more than he needs to. So he doesn't need to fence it on the river. We can still use the same diagram over here. What's the least amount of fencing that he needs to buy? Okay. What's the least amount of fencing? So I always recommend starting with your primary equation, right? That is what is being optimized. We are trying to minimize the amount of fencing, okay? Which normally would be the perimeter. But remember, we're not going all the way around. So what would the fencing equation be? W plus L plus W, right? So I'm going to call that F for fencing. How about that? And it's going to be 2W plus L. So that was actually the constraint in the previous problem. Yes, we set that equal to 500. But now it's our primary equation. I want to take the derivative of that, set it equals 0. But again, I have the fencing in terms of 2 variables. So now we go to the constraint. The constraint is going to involve a number. I want the area now to be at 10,000 square inches. So you could say the area is length times width. This is our constraint equation or the auxiliary equation or the secondary equation. You could even call it A if you want. A equals length times width, but we know that that is going to equal 10,000. So you really don't even need to call it A. What we want to do is write it in terms of the number, okay? All right, so from there, we just need to solve the constraint equation for either variable and then plug it into our primary equation. So what do you consider? You consider which variable is easier to solve for. It's probably just as easy for either one, right? L or W. And then what are we going to do when we plug it in? Do you want to plug it in and double it? Ooh, or do you just want to plug it in? Yeah, I just want to plug it in. So I'm going to solve for L over here. So L is going to equal 10,000 divided by W. I'm going to box that because, again, I might need to come back to that if I want to find the length. But for now, I'm plugging it in right here. So then I get the amount of fencing is going to be twice the width plus the length, which is 10,000 over W. So now if you want, you could actually call that F of W if you want. It is a function of a single variable. This is also the time where we get our relevant domain. My arrow's kind of in the way there. So we can typically put a comma. You could do it as interval notation or inequality notation. Now notice the equation itself has built in the fact that W can't be 0, right? Which we know that. The width can't be 0 because if the width is 0, he said he's just rolling out the fencing along the river. It doesn't enclose anything. So what would be the largest the width can be? Well, that's going to be kind of harder to figure out here. The width is going to be the largest when the length is the smallest, but I don't want to make the length be 0 because then if I try to figure it out, it's going to be 0, right? So sometimes really all you need for a relevant domain is just kind of like a ballpark. There's not necessarily an upper bound that we have to hit. Like when we did the fencing yesterday, Jackson said 500, but then I reminded y'all that we can go out and come straight back, so we could have narrowed it down to 250. 500 would have been fine as well, okay? So in this case, we just want our width to be a positive number, okay? So really no upper bound. Now let's take the derivative. Well, do we need to rewrite the second term? Yeah. You want to do it in your head? Maybe, maybe not. I think I'm going to write it as w to the negative first, just so I can see it. All right, so here we go. F prime or f prime of w, or the derivative with respect to w, is going to be 2 minus 10,000 w to the negative second. And now we need to clean that up because we got to use it. So that's really 2 minus 10,000 over w squared. Now that's not a bad version to use, but remember from the previous sections, I said, bless you, because we're going to use it to find where the critical values are, and possibly for a number line chart. If you ever have multiple terms and at least one of them is a fraction, it's probably best to get it as a single fraction. Okay, so let's take a little bit of time to do that. The common denominator is w squared, right? So if I multiply the first one by w squared over w squared, I get 2w squared minus 10,000 all over w squared. Okay. Now from there, if you want, you could factor out a 2, and that gives you w squared minus 5,000. Now that's a difference of squares, right? But is 5,000 a perfect square? Major, how are you?
Good, how are you?
Doing well. I'm going to leave it like that. I don't want to factor it as w minus the square root of 5,000 w plus, but I could. So that's good enough. Now, let's consider where it's d and e. F prime is d and e when the denominator is 0. That's when w is 0. Not interested in it here, right? Not interested in it. So let's just go ahead and set it equal to 0. So that would get a check right there. It's equal to 0 when the numerator is 0. So let's go ahead and do that. That's when I'm not going to even bring the 2 down. So that's when w squared minus 5,000 equals 0, or when w squared equals 5,000. And now if you take the square root, you get negative square root of 5,000 or positive square root of 5,000. We still want to consider both. Do both of them make sense in the context of this problem? No, we don't want a negative one. So once again, we have a single critical value in our relevant domain. That's the only positive critical value you have. 99 times out of 99 3/4 of the time, that's going to be the answer that we want. So if you didn't have to justify, go with that right there. Now that's not necessarily the answer, but that's the quantity that's going to optimize the situation. So now we need to just answer the question. What did it ask us? What is the least amount of fencing? So from here, I can take the w if I wanted, and I can plug it back in over here to find L if it asks me for the dimensions. But I can also plug it back in right here to find the fencing. Yes? Now, you could find L first and then use L to find the fencing in the original equation, but you don't necessarily need to. From that single value, I can go in several directions depending on what it's asking. It's asking me to find the fencing, so I'm going to plug it in over here. All right. So answering the question, the least amount of fencing is, and I'm just going to plug it in right there. Like if it were a free response, I'm going to plug it into 2w. So it's 2 square root of 5,000 plus 10,000 over the square root of 5,000. And then what units did I put there? Inches, right? Inches. Now I don't need units down here on the end of the computation because I'm answering the question and they're there. But if you want to, it doesn't hurt to add them there as well. So I didn't even really need to find L. L would be 10,000 over that number. That's really the second one there. So that's it. That's it. Okay. And of course, if we wanted to justify, I told you how to do the modified first derivative test, modified second derivative test. I'm not going to do that here. Now, is the square root of 5,000? It's not even a perfect square, I don't think, right? No. We can factor 100 out of it, which is a perfect square. It's going to be an irrational number. So if you're the farmer, can you even go buy that amount of fencing? That would be a cruel joke to go to the Ladybug supply store and tell the guy, hey, I need that amount of linear fencing. No more, no less. I don't want to spend more than I need to, and I really need that amount. And it's like telling a guy to cut a 4-foot board pi feet long, right? You're not going to be able to do it. It's an irrational number. So I guess if you're the farmer, what do? You go to the next finite value smaller than that, or the next finite value bigger than that?
Yeah, you go to the next hardware.
You go to the next hardware store, right? Yeah. Irrational ladybug farming supply, right? That just may be where the employees are temperamental, right?
Right.
Yeah. Like the ladybugs themselves. So I said I wasn't going to work that problem, but I went ahead and did it, right? Because it was a good one, right? It was a good one. Now, in the notes, I'll tell you which ones in the notes I want you to do and which ones I don't want you to do. I'm sorry, in the worksheet. But we'll do that at the end, okay? Any questions on this? All right. So notice again, the endpoints didn't make sense. In a lot of these geometric problems, the endpoints collapse the structure down to nothing, and they end up being the opposite of what we want, okay? But sometimes the endpoints are relevant, okay? When are the endpoints relevant? Well, just kind of a clue. If it ever asks you to find a point that is closest to a graph, that's where the endpoints are relevant, closest to. Keep that in mind. Endpoints are relevant on the closest to, because, you know, if you only find the critical values there, that might not be the answer. It might be one of the endpoints. So you got to be careful. All right. So let's look at example 5. Find the point on the curve y equals x squared that's closest to the point 3, 0. All right. That seems pretty easy. How do we know reading that that's an optimization problem? I don't see anything about ladybugs. Closest. There it is. Superlative case. So we're trying to maximize closeness, right? What's the formula for closeness? What the heck? How do we, yeah, right. How do we maximize closeness? Right. So what, right. And while staying on the graph of y equals x squared, how do we measure that? Is there a closeness meter that we?
Oh, it's absolute value? No, it's not.
How do we measure closeness? Distance. Thank you. Thank you. That's what I'm looking for. We have to have some quantifiable thing. To maximize closeness, we're really going to minimize the distance. There you go. We're going to minimize the distance. Hoorah, right? Minimize the distance. Okay. Yeah. Oh, sorry. Sorry. Aiden, look in here. Find yourself. We got you a small, right? So one of those is a small in here. You can grab it. I'm going to keep going. And thank you again for your artwork. We'll get you the artwork fee. Yeah, when I see Devin. All right. So now I need to minimize distance. A picture here will also help. Okay. Especially since they're giving us the equation of a curve. So let's go ahead and sketch y equals x squared. All right. So y equals x squared. How about in red? There and there. There we go. Y equals x squared. You got it. Thanks again. They turned out fantastic. And Big Frog had a little bit to do with that. Most of it was Aiden Grenier. Yeah, nice. Okay. Yeah, so there it is. And now I'm going to put the 0.30. I'm going to put it about right here. Okay. That's the 0.30. So I can kind of do the eyeball test. I want the point on the red graph that's closest to the blue point. I think, let's see. If I go straight up here, that's when x equals 3, right? Is it going to be any point to the right of 3? Like, is this point going to have a chance to win? Or is this point going to have a chance to win? Or this point? No, no. But it could be straight up, right? Maybe, maybe. Remember that might straight up, right? To the p, positive p to the p power, straight up. My graph is not necessarily drawn to scale, but it could be straight up. Now, I know that it's not going to be to the right of straight up. Now, it could also be straight over here to the left. Maybe this point when x is 0 is the closest point, maybe. But is this going to be the closest point to the left of 0? No, those are further away. So if you just draw these little points straight up and straight left, that's not a saying, is it? Yo, straight left, right? You kind of get an interval. It's going to be either x equals 0, x equals 3, and nothing to the left of 0, nothing to the right of 3. But it could also be, yeah, some point in between there, right? Right. And again, my graph is not drawn to scale. So what you want to do is just kind of draw an atypical result, not the extreme point, not the end point. So let's just call that point on the parabola xy. And now I have something that I can work with. I'm going to draw the line from the random point xy on the parabola to my fixed point 3, 0. And I'm going to label the length of that beefy brown line big D. Okay. So if I'm trying to minimize distance, let's go ahead and write our primary equation. That is the thing to optimize. Y'all remember the distance formula? The distance formula is the square root of the change in x squared plus the change in y squared. It's really just the Pythagorean theorem solved for the hypotenuse, which is the distance, okay? So do you have to have that memorized? Of course, but you don't have to rememorize it because you already have it memorized. See, that's the good news. So let's go ahead and write it specifically here. Square root of. I'm going to do my first point. I'm going to do x minus 3. That's the change in the two x values squared, plus the change in the y values, y minus 0 squared. I'm going to keep it corresponding. X first, y second. But because you're squaring it, it could be flipped around. But it's good to kind of keep those good habits. All right, there it is. Now, if I simplify that, I get the square root of x minus 3 squared plus y squared. Okay, looking good. I need to take the derivative of that and find critical values, but it's in terms of two variables. I have the distance in terms of x and y. So I need another equation that relates x to y, and it's going to involve the constraint. What's the constraint? What's preventing me from getting up in there right in 3's face and saying, is this close enough for you? Is this close enough for you? What's preventing me from getting right up in there? Yeah, it has to stay on the graph, right? It has to stay on the graph. Do I know the equation of the graph? Oh, y equals x squared. Okay. So in this problem, the constraint is handed to you. It's y equals x squared. All right. Now, do you want to solve that constraint for y or for x? Probably for y, right? Because it's already solved for y. So let's plug it in. So we get the distance formula is now x minus 3 squared plus y squared, which is x squared squared, or x to the 4th. Ay, caramba. Okay. All right. Now that I have it in terms of a single variable, it's time for the domain. What's the domain? Well, if you hadn't done it already, you want to draw the picture and draw your straight up and straight left lines, and it's got to be between 0 and 3. But unlike the previous problems where the endpoints collapse to geometric shape, 0 and 3 are viable candidates, right? Again, my graph is not drawn to scale. It could be the endpoint. So for the first time, we have a closed interval, which means we're probably going to be able to use the EVT if we have to justify, okay? So now we just need to take the derivative and set it equal to 0. Oh boy, how much fun is this going to be? Tons, right? Let's go for it. D prime is, the square root is everything to the 1/2, right? Yeah. So here we go. It's going to be 1/2 times all of that to the negative 1/2. All of that is just x minus 3 squared plus x to the fourth. Okay, that's good. Times, I'm going to switch flavors here. Beefy blue. Times the derivative of the radicand, right? The inside, which by the chain rule is 2 times x minus 3 to the first times the derivative of x minus 3, which is 1. That's nice. Plus the derivative of x to the fourth is 4x cubed. All right, got some chain rule going on there. Now let's clean it up before we use it. D prime is, I know I'm going to have a denominator, so let's build that shelf. This whole piece here, that's going to end up in the denominator. The 1/2 makes it a 2 down there, and then I'm going to have the square root of x minus 3 squared plus x to the fourth, right? Now what ends up being in the numerator? The derivative of the radicand, right? Which if I distribute is 2x minus 6 plus 4x cubed. This is the radicand derivative. Okay, now remember, critical values can come where the denominator is 0, but in these applications, those are the values that make that are impossible, physically impossible. Okay, so we really just want to set the numerator equal to 0. So if I set the whole thing equal to 0, that's going to be when 2x minus 6 plus 4x cubed equals 0. So notice what I ended up setting equal to 0 is just the derivative of the radicand. I'm going to come back to that here in a second for a good reason. But right now, I'm focused on trying to solve this. Now, let's say that you're faced with this on a real test. And let's say it's a non-calculator test. Do we know how to algebraically solve this? If you want to write it in descending order, 4x cubed plus 2x minus 6. That I could factor out a 2. Okay, that would not be bad. 2 times 2x cubed plus x minus 3. That's a good start, but it's not a cubic. I mean, it's not a quadratic trinomial. It's a cubic trinomial. So that's going to be a little harder to solve. So here's the deal. And this is the truth. This could appear on a non-calculator portion of the exam. And if you can't solve it algebraically and it's a no calculator portion of exam, guess what method you might have to resort to? Guess and check. Guess and check. Yeah. That's still a viable method. It's one of the more primitive methods, but it still works. If you have to get off the island, yeah. Now here's the deal also. If it's going to be a guess and check, the numbers that you need to try, one of them is going to work. 1, -1, 0, maybe at the most 2, -2. It's not going to be like 7.65, right? You're going to try 0, 1, -1, 2, -2. So let's try 1. Let's try 1. When x equals 1, you get 2 times 2 plus 1 minus 3, which is what? It's 0. Ah, it's x equals 1. It's x equals 1. Yeah. Right. It worked. Okay. Now, if you did have a calculator, then this would be a no-brainer. You would pick this up right here. You would graph that in y1 on the window from 0 to 3, and you would look for the x-intercept. Okay. Now, could there be another critical value somewhere between 0 and 3 besides 1? It is a cubic function after all, right? Yeah. But the way these problems are structured, they're not going to make 2 of them there. If there were 2, you would just try them both out, right? We haven't seen an example where there's 2 critical values, but if that's the case, you just plug them both in and see which one is either the smaller or the larger, right? Now, just for review, I'm going to show you how we can figure out what the other factor is. I'm going to come to this right here, 2x cubed plus x minus 3, and I'm going to do synthetic division. We did that when we did limits, right? So you don't necessarily have to know this, but it's fun. We have a 2x cubed. We have a 0x squared. We have a 1x and a -3. So what I'm doing is I'm writing the coefficients down of the cubic polynomial in descending order with a placeholder. I know that 1 is a root. X minus 1 is a factor. So I'm going to put a 1 right here, and I synthetically divide. In this last box, I should get a 0. This is also called synthetic substitution. And I already know when I plug in a 1, I get a 0. So I bring down the 2 by gravity, and then we multiply on the bottom and slide it up. 1 times 2 is 2. Slide it up to the next column, you get 2. And remember, you add in these columns, so that's 2. 2 times 1 is 2. Slide it up, add. 2 plus 1 is 3. And of course, 3 times 1 is 3. You add them and you get 0. These are the coefficients of the depressed polynomial. Depressed, why? Not because it's in a math class. That's what saves it. It's depressed because it's 1 degree smaller. So basically, we know this. This is what we know. We know then that 2, oops, I don't need parentheses. We know that 2x cubed plus x minus 3. We know 1 is a root, so x minus 1 is one of the factors. And guess what the other factor is? 2x squared plus 2x plus 3. Okay. So again, this is just extra stuff. You're not going to have to do this. Now, if I can factor 2x squared plus 2x plus 3, and there happens to be another root of that between 0 and 3, I want to find it. But it doesn't factor. And if you use the quadratic formula, negative, remember the quadratic formula? Let's look at this. X is the opposite of b, so it's the opposite of 2, plus or minus the square root of b squared, so that's 2 squared is 4, minus 4ac. A is 2, c is 3, all over 2a, that's over 4. What type of number do you get under the radicand? It's called the discriminant. A negative. If you get a negative under a square root, guess what types of solutions they are? They're imaginary. Yeah. So all that work just to find that there's no gold in this here mine, right? No big deal. Hi, Coach Fair. So anyway, we found the one real solution. The other two are imaginary. So this was just an adventure, a good review. All right. So now that we found x equals 1, what do I do with it? X equals 1 is right here. Do I know for sure that that's going to be the closest distance? No, because the endpoints are relevant, right? So now it's the EVT time, right? Now we play the game. What is the distance at 0? What is the distance at 3? And what is the distance at 1, our critical value, right? This is the game, right? Called Extrema, right? Who's going to win? Which two contestants leave with a broken toaster, right? Well, we're going to plug those back into here, right? That's the distance formula in terms of x. Now, to save a little bit of time, I don't think I need to plug in a 3 and a 0, because what is this distance here? It's 9, because that's just the function value of x squared at 3, right? You get 9. 3 squared is 9. What's this distance here from 0 to 3? 3, right? So you can see that my graph is way out of whack, right? My graph appears to have 9 equaling 3 distance-wise. You see that? Everyone okay with how I got 0 and 9? Now, if you're not sure, you could plug those into the distance formula as well. But what I really need to do is plug the 1 in there. So this was we said this was 3 and this was 9. Let's plug a 1 into this boxed answer here. I'm going to get 1 minus 3, which is -2. -2 squared is 4. So I end up with the square root of 4 plus, what's 1 to the 4th? 1. So what's 4 plus 1? 5. So here are my 3 distances. 3, square root of 5, and 9. Which one of those is the smallest? Square root of 5. Okay. So it turned out that the critical value was still the winner. But there are questions where one of the endpoints is still smaller than the critical value. So in your closest two questions, in your distance questions, you can play the EVT, you want to consider the endpoints, okay? But in the geometric problems where you have shapes, they'll collapse down. Okay, so this is your justification right there. And now you'll say, so, and now did it ask for the distance or did it ask for the point? Find the point on the curve, right? So the closest point is 1 comma, is it 1 comma square root of 5? It asks for the closest point on the graph. All right, here it is. This is the point 1 comma, I don't want the distance to 3, 0. I want the y value on the graph. What's 1 squared? 1. Yeah. So the closest point is 1 comma 1. See that? Answer the what type of question? Frickin'. Answer the frickin' question. Yeah. Yes. Yeah. It asks you for the point on the curve. So right here, when x is 1, we know that this distance is the square root of 5. But what is the actual point on the parabola? The parabola's equation is x squared. So right here, this is the point 1, 1. The point 1, 1 is closest to the point 3, 0, and the distance happens to be square root of 5. So that's why I'm saying when you find your optimal value, which is just a single x value, did it ask for the y value? Did it ask for the x and y value? Did it ask for the distance? Okay, all kinds of quantities that are related to the optimal value. Okay. Yeah, now if this were a multiple choice question, square root of 5 would be an answer for sure. Okay, and if you answered 1 comma square root of 5, all this work would be for nothing. But as Ellery said, if it were a free response, man, you would be earning points all along the way, and then you would just lose on that final answer. Okay. Oh yeah, that would be you after answering square root of 5.
Exactly.
Yeah. Okay. So answer the freaking question. Answer the freaking apostrophe question. Because I want you to get credit for what you've done. All right, so this is just a summary of how to justify if it asks you to justify. This is enough justification. When it's a closed interval, when you show the critical value computation, we find them ourselves and we declare them by x equals down here. And then you compute the y values at all the interior critical values in the endpoint. That's the justification, okay? You don't have to say, I mean, if you wanted to, you could say since the square root of 5, is less than 3, which is less than 9, comma, the closest point is that, okay? If there was any kind of, analysis to show, it would be that number is smallest of all 3. But typically you don't have to do that. Might that be a standard they implement this year? Perhaps. I know on one of the questions they asked who lived closer to school, Karen or Larry, and we computed both their distances separately. And Larry lived like 7 miles away, so we got 7 miles for his computation and 5 for hers. And that year, if you just said, so Karen lives closer, you didn't get credit. You had to say, since 5 is less than 7, comma, Karen lives closer. So again, you want to lead that horse to water, and you want to salt his oats, and then you want to stick his face in the water and say, drink, drink, and then you scoop it up into his mouth and tilt him, and then jump up and down so it goes down. You're going to make that caller drink.
The horse's college board.
Yes. You're going to get that water in the freaking horse.
What they do in Suits.
Suits?
Yeah.
Oh, I haven't seen that show. Okay. All right. Okay. I will check out Suits. All right. All right. So far, so good. Let's move on. Example 6, if you want to work that on your own, that's a supplementary problem. Yeah. I think, you know, the endpoint might be the answer to that on that one. All right, example 7, moving along. I always forget, 1205, okay. Example 7, find the dimensions of the largest rectangle that can be inscribed under the curve of y equals 16 minus x squared in the first quadrant. Classic question, okay? How do we know it's optimization? Largest, okay? Largest. Is this one for which we could draw a picture? Yeah, sort of. We're trying to fit a rectangle under the graph of 16 minus x squared in quadrant 1. I think we could draw it. So first thing we're going to do is draw the curve y equals 16 minus x squared. I'll do it right here. And again, this could be a no calculator question. So we know that 16 minus x squared is the graph of a what? Parabola opening down with a y-intercept at 16. Good. So there's 0, 16. And then it opens down like a frown, right? And just for kicks and giggles, do we know where the x-intercepts are? Just kind of at a glance, where the 16 minus x squared would equal 0? 4 and -4, right. And if you weren't sure, you could go off to the side and say zeros, right? 16 minus x squared equals 0. 16 equals x squared. X equals plus or minus 4. Yeah, so this is -4, and then this is +4, for what it's worth. Those might come in handy. All right. Now, it said find the dimensions. Okay, so I'm walking away with the length and width of the largest rectangle that could be inscribed, bless you, under the curve in the first quadrant. So, oh, that's important too. So here's the first quadrant. Let me highlight it. And now you want to draw just like a representative rectangle. You don't want it to be the extreme case. So is this a good rectangle to draw? Ah! No, no, because I know it could be bigger than that, right? Here's what's probably going to happen, right? If you're going to draw a rectangle, it's going to be as big as possible. It's probably going to have 2 of its side lengths on the axis itself, right? And then it's going to expand to contain a vertex, right, on the curve itself, something like that. So there's a representative rectangle. Now, it could be that it's going to be this tall, skinny one, or it could be that it's going to be this short, squatty one. But I don't want to draw one of those extreme cases. I just want to draw kind of one in the middle, all right? Now, I need to label the dimensions. So we used L and W on the ladybug problem, but I think we could do better than that here. This is a random point X, Y. So the width could be X and the height could be Y. We're on the coordinate plane now. All right, so when it says the largest rectangle, what is it that we're trying to maximize? Area, perimeter, what? Yeah, it's implied to be area. It takes up more space. So we're trying to maximize area. So let's write an area equation. I'm going to write area is A equals, and then length times width, right? Which for us is XY. Okay, cool. There's my primary equation. That's the one I want to take the derivative of, but oh, alas, I cannot. I have it in terms of both X and Y. I need it to be in terms of a single variable. So what is the constraint? Once again, it has to be contained under the curve of y equals 16 minus x squared. So that is the constraint. I didn't have to go write it myself. Now, do you want to solve that for y or x? A tee. Yeah, let's solve it for y. And it's just as easy to plug in for x or y. So that's awesome. So I'll box this. I may, bless you, need to come back to it. We'll plug it in there. So we get area equals x times 16 minus x squared. And now we come up with a relevant domain. So we go to our graph. What's the smallest x could be? 0, right? Now, can x actually be 0? No, because if x is 0, we collapse the rectangle down to a 0 width. And that would be a minimum area, wouldn't it? So I'll do interval. X has to be greater than 0, but it has to be less than what? 4. Ah, see, I knew that x-intercept was going to come in handy dandy. But it can't be 4 because when it is 4, I collapse the height down to nothing. All right. Landon's not here today, so if y'all want y'all's t-shirts for the weekend, I might have to take y'all on faith, trust that you ordered, or yeah. Okay. Because y'all want them for the weekend. I know that. All right. So anyway, from 0 to 4, 0 to 4, there's our relevant domain. We need the derivative. You want to use the product rule, or do you want to distribute first? Yeah, I'll distribute for sure. 16x minus x cubed. Okay. Now we're going to get the derivative of a with respect to x, right? Or a prime of x, whatever tickles your fancy. So here we go. 16 minus 3x squared. Nice. Is it ever undefined? No. Is it ever 0? Maybe. Let's set it equal to 0. That earns a check, right? Now we solve. 16 equals 3x squared. Looking good. Divide through by 3. We get 16/3. Is it going evenly? No. So now we take the square root, plus or minus. Do we want the negative one? No, we don't even really need to write it down, but you can, right? Negative square root of 16/3, and you say, I don't think so. And then x equals square root of 16/3. Now, is that between 0 and 4? Man, I sure hope so. 16/3 is about what, 5-ish? And then the square root of 5-ish would be 2-ish. Yeah. So this is 2-ish, right? To 3 decimals, 2.ish, right? 2-ish. So it's in. So again, we know that's going to be the answer, right? Because not only is it the only critical value on our interval, but we've already seen that at the extreme, when x is 0 and 4, the area is nothing. So somewhere between it going from, a super tall, skinny one that has very small area, the x gets bigger as y gets smaller, the area is going to be positive, and then it's going to eventually return to 0, right? So it's going to go from 0, it increases up to a max, and it decreases back down to 0. And we found the critical value. So that's it. That's the Holy Grail. So now we box it up. There are no units, and we get full credit, right? No, answer the freaking question. Answer the freaking question. At Fuqua. I don't know if that's going to catch on. Okay, at Fuq. At Fuq. Yeah, what'd you say? That might, yeah. The Q has a cuss sound, right, doesn't it? You better not say that, though. All right, it asks for the dimensions. So dimensions are length times width. Well, we already know the x value. How do we find the y value? Plug it in here. Now, if it did ask for the actual area, remember we have 2 different area equations in terms of x. Okay, so this would be to find a, and then we plug in here to find y. So let's do that. So we're plugging in a number. So we'll say when x equals the square root of 16/3 colon y equals 16 minus, what's the square root of 16/3 squared? 16/3. Yeah. Now, if it was a free response, there would be no reason to simplify that, but I think I wanna. All right, that's 16 over 1. So 3 times 16 is 48. 48 minus 16, 32/3. And there are no units, right? So if I box this and I box this, if I box them both, is that enough to answer the question? Oh, that's kind of squirrely. Squirrely. So the optimal dimensions are x equals the square root of 16/3 and y equals 32/3. There you go. And there are no units. So that's it. Answer the freaking question. And now if it wanted the area, since you had both of them, like if it asked for the dimensions and the area, instead of plugging your x value into one of these, since you have both dimensions, you could just multiply those 2 together. Okay. What time? I never know. I never remember. 12 minutes. Okay. Thank you. All right. We didn't have to justify, didn't ask, so I'm not going to, okay?
Optimal is a flavor word. You don't have to use it.
Optimal is a what?
Like a flavor word,
A flavor word?
right?
Yeah,
I don't know if that makes sense.
yeah. Oh, yeah. Adjective.
It's
Yeah. Yeah. So, yeah, if it asks you for the dimensions, you could just say, so the dimensions are. Yeah, absolutely. Absolutely. I threw optimal in there because we're doing optimization. Yeah. Now, what you don't want to do is throw a flavor word in. I like that. Adjectives are flavor words. You don't want to throw a flavor word in there accidentally and say, so the minimum dimensions is, and use the wrong verb too, right? The maximum dimensions are, the optimal dimensions are, or just the dimensions are. I like that. Keep it engineer-like, right? Okay, good. So if you want to read this, these are steps to an optimization problem. And I just want to remind you that the last step, if you're not already doing it all the way through, to smile, okay? And look at number 9, answer the question in a complete sentence using appropriate units. Okay, good. This just summarizes the other 2 ways to justify in the absence of endpoints. You got to say for all, okay? Those are global arguments, for all. And again, you can use the capsize capital A for all. All right. Open top box, that's kind of a classic one, but I'm going to skip it. Let's see. We got 2 more to do here. It is a Friday. Example 9 that we're not going to be able to finish. Example 11 is really, really good. So instead of spending 2 days on it, we will spend 3. But what I'll do on Mondays, when we finish these 2 examples, I may work example, since we'll have time, I may work example 10 as well. Okay. Now let's quickly look at the worksheet. What are some of the ones on the worksheet that you can omit? Okay, I'll show you because it is a beefy worksheet. Beefy. All right, so omit number 1. 1 is out. Right? Yeah. Okay, so worksheet 3.6. Omit number 1. Omit number 6. This is on the website, by the way. Yeah, this is on the website. Omit number 10. Omit number, Mr. Wenzel has a big problem. You need help with that one. Omit number 13, that's Farmer Tate. Now, after Monday, I may be able to reassign that one because I was going to skip that example. But for now, skip it. Example 14, you can skip. 15 is just too good. I'm on a ladder falling. 16, my daughter's building a motel for her ladybugs, very similar. 17 is closest to. 18 is like the Toga Boys. 19 is Toga Boys. 20 is a fantastic question. I love question number 20, but you don't have to do it. It's way beyond the scope of College Board. Okay. So I don't know that, that trims it down a little bit, but you can start working on those this weekend if you want, because you have enough information, but you're also finishing up 3.5. Okay. Now we'll stop there. And then if you know what size shirt you got, we can write it down. Any questions?